All right, section 11.5, vectors in the plane. So, like I said, this is like a super quick overview. You're either going to find it really fast or be really bored. Either way. But first of all, what is a vector? Can anybody who knows what a vector is tell us what a vector is? And there's different ways you can answer this question. So, Kim.
It's a line in direction.
Yes. Nice. It's a directed line segment. So it is a segment. There are two, there's a start and a finish, but it has a direction. So, you know how normally, like if you've never seen vectors before, remember rays? Because that looks like a lot like a ray. So remember rays, it's not a ray. A ray has an initial point and then goes in the direction of another point. I could call this ray AB. And we also had that notation AB. This is not a ray. Vectors are not rays. Vectors are not rays. When you draw a vector, like I said, there will be a start and an end. And notice my arrow is ending right. I don't know if you can tell there's an end point right there. But there's an end point. We call it a terminal point. So this is a vector. And I will call this P and Q. P is an initial point. I always find this backwards. It makes sense with the picture, but sometimes it's also known as the tail. You'll hear people talk about heads and tails of vectors. The Q is called the terminal point. Also known as the head. But notice the vector ends at point Q. It does not extend beyond point Q like we do with a ray. Whoops, you can't see it. So, not a ray. Rays have an infinite length. They go on forever. Vectors, stop. That's why we call it a line segment, but it's got a direction. Can anybody else tell me anything else about vectors? So, vectors... Oh, Royce? Say it again. Another two-dimensional point? Plane, yeah. So, we're drawing the vectors on a two-dimensional plane. You actually could have vectors going in 3 dimensions. We're going to stick in 2. I don't know, in physics, do you guys get into 3 dimensions? You stay in 2 also? But yeah, you actually could. You could have 3 dimensions. So we are going to do 2 dimensions. And so because of the 2 dimensions, here's just some notation. We'll put it here. So there's different ways that you'll see it. If it's in a textbook, a lot of times vector PQ will be in bold. It'll have the PQ, but they'll be bold. It's hard to do bold when you're handwriting. So then you'll see the arrow. And some people put the little half arrow like I just did. Some people put the full arrow. Some textbooks just put the arrow on anyway. It's like there's no one set standard. I'm going to do the half arrow. That's just what I learned, and so I do it. You can also, because the direction of a vector in 2 dimensions, we can talk about the horizontal direction and then the vertical direction. There's a horizontal and vertical component, just like there are for coordinate points. But instead of parentheses for coordinate pair, we use angle brackets. Looks like a less than or greater than, but they're actually slightly more stretched out. Again, your handwriting is not going to be perfect. But there's a vertical component, which I'll just call a horizontal component, and then a vertical component. I'll describe more when we get into drawing some pictures. That's not vertical. So the first component, just like xy, x is your horizontal. So the first component is always your horizontal component. And then we have the vertical component. And in general, vectors, we use vectors, and we're going to look at one, maybe two application problems really quickly at the end. They're going to be pretty basic. Well, one of them will be pretty basic, one of them may not. Anyway, but we use vectors in physics because this directed line segment, so vectors have a direction and a length. The direction, like forces, for instance. You're pushing in a certain direction, or there's a certain force pulling on something in a certain direction. So a vector can represent that force because it can indicate the direction that the force is acting on the object. But it also, the magnitude of the force is represented by the length of the vector. You actually don't really have to know that for the calculus part, but that's the, vectors actually have a huge application in physics, and they're very useful because of that. So vectors have a magnitude, which is indicated by the length of the vector, and a direction. All right. So let's just look at some examples of like how you can use vectors in a diagram, because we know that it's nice to actually be able to model real-life applications with some sort of diagram. And vectors can do that for us. So, let's just say I have vector v, which is has a horizontal component of 3 and a vertical component of -4. So this is one way to notate a vector, using a horizontal and vertical component. And you'll see this done in two different ways. One is just kind of floating out there. Start at some random point somewhere, wherever you want. And from that point, we're going to go 3 units in the positive horizontal component, or positive direction, and then 4 units in the negative vertical direction. And what color was I using? There's my terminal point, and there is my vector. A lot of times, though, it helps to put vectors on a coordinate plane. It really depends on the problem. If we put it on a coordinate plane, then most often, I shouldn't say most often, but often, it can help to put your initial point at the origin. Actually, I'm not going to label that as B. We don't have it. But then I'll go positive 3, negative 4, and that terminal point ends up at the coordinate pair of 3, negative 4. So this is vector V. So you'll see it done both ways. The vector can be drawn just with no reference, or it can be put on a coordinate plane. But it doesn't matter. It kind of depends on what you're going to do with it. Another example here. Let's say that vector V has an initial point. I'm going to make a little table here. Vector V has an initial point at, I don't know, how about 1, 5. And vector U has an initial point at negative 3, 2. And then they have terminal points. Let's say that vector V has a terminal point at, how about 3, 1? And then vector u has a terminal point at -1, -2. So let us... Oh, actually, you know what? For fun, let's put vector w. Oh, I know, right? Getting crazy. Let's put vector w with an initial point at -1, 1. And then let's say its terminal point is at -3, 5. All right, let's just draw these and see what they look like. So what do I got to do? I got to get up to 5 on the y, -2. Okay, I can fit this easily. I made the number small enough. So let's go ahead and just plot all those. So you guys go ahead and draw them, and then we'll talk about what we get. So 1, 2, 3, 4, 5, 3, 1. There's v, there's u, and then -1, 1, 2, 3, 1, 2, 3, 4, 5. So you should have wound up with a picture like this. Any questions on the picture? Nothing earth-shattering. Anybody notice anything in the picture? Lots of different things we can say in this picture. They all have the same slope, so they are all parallel. V, W, U are parallel. Are they all going in the same direction? Oh. In fact, actually, some people use, when talking about U and W, they're parallel, but they go in opposite directions. Some people use the term anti-parallel. Your book doesn't. We won't bother getting into anti-parallel, but just so you know, there is such a thing as anti-parallel. What do you think? Are any of the vectors equivalent? We haven't really talked about what makes vectors equivalent. So remember, because vectors really can be drawn anywhere, do any of these two vectors have the same direction and the same magnitude? Do all three of them have the same direction and same magnitude? So which two have the same direction and magnitude? U and V. So we call U and V equivalent vectors. U and V are equivalent because they have the same direction and magnitude. All right, let's see. Speaking of magnitude, let's look at a formula to calculate magnitude. Any questions so far? This is going to be like random stuff about vectors today. Let's use I'll make a new one. Does anybody need this old problem? I was going to use the old one, but let's just make a new one. Let's say we got vector v that has the components of, let's do 3, 4. Find the magnitude of vector v. which, by the way, there is notation for magnitude. Notation looks like double absolute values. That indicates magnitude. So when it says find magnitude, that's like finding the length of the vector. Well, if we draw a quick picture, I think it will become obvious with this one, if you don't already see it. If I start from the origin, vector v says go to the right 3 units and up 4 units, and we have this. Can you guys tell me how long vector v is? It is 5. Because it's Pythagorean theorem. You can make a right triangle out of it. So the magnitude of vector v is, now I'll just put it here so we have it as a reference. It's just 3 squared plus 4 squared in a square root, which, that's Pythagorean triple. We know that one. That's 5. So in general, we have a formula. Pretty straightforward formula because it is just Pythagorean theorem. If you have vector v with the components v1, v2, then the magnitude of vector v is the square root of v1 squared plus v2 squared. Any questions there? Aight. What else we got? How about if I gave you this problem? Find the horizontal and vertical. What are you doing there, Tanner? You've been on your phone for like the past 10 minutes. Yeah, what are you doing, Karen? Liar? Put them away. Careful or I'll give away the Wordle. Dang it. I don't know Semantle. Okay, well, I'll have to look at it later. Yeah. Square word is another fun one that somebody showed me, so now I make that a daily game too. Worldle? Weddle. I don't know Weddle. What? Oh, I'd suck at that. Patrick Ewing, that's a football player, right? Just kidding. I know, that's basketball. My brother went to Georgetown, actually, with Patrick Ewing. Find the components. What was my problem I was going to give? Of a vector with an initial point. Somebody give me a number. Give me another one.
8.
And a terminal point. Don't worry, I'm going to use 8, and I heard 3. Okay. And a terminal point. Let's make some negatives in here. How about -8 and -3? All right. Let's call these points. Let's label them. We'll call that first point P and the second point Q. How do we do this? Yeah, just subtract. Which way do we subtract, though? Because it does matter. Exactly. So if I do a quick sketch of them, I'm not going to draw it to scale, but we can get a rough idea of which way to subtract. So 510, we'll just put up here. I'll say that this is point P at 510. And then point Q, -8, -3, I'll just put here. So your vector is pointing in this direction. Is your horizontal component positive or negative? Right. Remember, going from point P to point Q, you would have to move left that's moving in the negative direction. So we need a negative horizontal component, and you can see that we're going to get the negative when we do -8 minus 5. If we did it the other way, 5 minus -8, that would give us a positive. So I think it was Gregory that said it, but you always do terminal minus initial for the components. So I'm not putting a formal thing here, but terminal minus initial. So for PQ, the vector, the horizontal component, I'm going to subtract the horizontal components of these 2 points, but doing terminal minus initial. So -8 minus 5. And then the same thing for the horizontal, or the vertical component, terminal point minus initial point. So PQ has the components -13. Oh, wow, -13, -13. That was not planned. And that makes sense. That seems logical. It does. We can see we're going negative in the horizontal direction and negative in the vertical direction. So, all right. Let's look at vector addition. Vector addition is very useful. Like I said, we use these vectors to represent things in real life, and if we want to like combine forces, we add the vectors that represent them. So, whoops. Good news is, it's pretty straightforward when you got components. Vector addition. You can do this algebraically or geometrically. We're going to look at both. Vector addition, let's just say that I have vector v, which is at v1, v2. Those are the horizontal and vertical components. Vector u, which is u1, u2, u1. Sweet. What did we win? So vector v plus vector u. What is your gut telling you? Because it's probably telling you the right thing. Yeah. v1 plus u1. Just add the corresponding components. And then v2 plus u2. So that's all you do algebraically. If you're going to do it geometrically, well, I know it's crazy. People call it head to tail. Some people call it parallelogram method. Whatever you want. Let's say that this is vector v, and I want to add a vector u to it. Imagine vector u, they call it head to tail because you draw them head to tail. So if they're drawn that way, then vector v plus w, or v plus u, starts where vector v is and ends where vector u is. And that is v plus u. If you're wondering why they call it the parallelogram method, you can actually make a parallelogram out of it. I know. So then, given vector v has the components 1, 2, and vector u has the components -1, 1, sketch. Oh, we didn't talk about that. Oh well, I'll use this to talk about it. 2v plus 3u. Now you don't have to put coordinates on there. You don't have to put an x and a y axis to do this. You can. You don't have to. But we basically just do the head to tail of these. So 2v means, and v is 1, 2, so I'm going to go, actually I might have to, I'm going to start down here just in case. So vector v over 1 up 2, there's a 1 vector v, but it says 2 of them, so I need to put 2 of them. So there's v and another v. And then it says put 2 vector u's. I'm going to actually put vector u on the other side. So vector u, starting from where I left off, head to tail, negative 1, 1, negative 1, 1, negative 1, 1. So this is v, v, u, 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 and then that would be vector 2v plus 3u. So that when they want you to do that, that's all they want. Does that make sense? If we had to find 2v plus 3u algebraically, that's not that hard. 2v plus 3u is 2 times the vector 1, 2 plus 3 times the vector negative 1, 1. This is called scalar multiplication. We're going to multiply the vectors by 2 or 3. But you literally just distribute. You multiply each component. So that becomes 2, 4 plus negative 3, 3. And then we know how to add them. Add the components. So 2 plus negative 3 is negative 1. 4 plus 3 is 7. And whoops, sure enough, if you look at what we got when we sketched, starting at the initial point for this linear combination, we go with negative 1 in the horizontal component and 1, 2, 3, 4, 5, 6, 7. What? It's like this stuff works or something. So, anyway. Any questions about that? All right. Got my little laundry list. We did addition, we did multiplication. Oh, unit vectors. This may seem silly, but it does have its uses when in application problems. So finding a unit vector. Find a unit vector in the direction of vector v, which has the components, I'm just going to make it easy, 3, 4. I kind of stepped on that Pythagorean identity, but a unit vector. Anytime you hear the word unit in math, what number should you think of? 1. So a unit vector is a vector with a magnitude of 1. So the formula for unit vectors in the direction of a given vector. A unit vector in the direction of a given vector with components v1, v2. We don't really have vector division, but it kind of works like it. But I'm going to write it like multiplication. We have vector scalar multiplication. You take the vector, oops, I'm giving the formula. So you take the vector v1, v2, and you multiply by the scalar 1 over the magnitude of that vector. And you can think of it as just divide all the components by the magnitude. But technically, like I said, we don't call it vector division. So if that's the case, can you guys tell me what the unit vector in the direction of this vector v is? That's exactly it. Because we can look at that vector and easily see the magnitude of it's going to be 5. All right, one more idea and then we'll get into a word problem. So one way of notating a vector is with its components, a horizontal and a vertical component. But remember, the whole point of vectors is they have direction and magnitude. So another way to notate a vector is to have its direction and magnitude right in there. So actually, I guess there's 2 ideas. I forgot one thing. It's at the bottom of my list. I should have had it on the top of the list. Before I get to the direction and magnitude thing, because it fits more in with our components, there are standard vectors. I'm going to make another example out of this one. Like I said, it's just kind of a hodgepodge of topics today, just so vectors aren't a foreign concept. Your standard vectors in 2 dimensions, we have vector I, which has the components 1, 0, and vector j, which has the components 0, 1. So another notation for vectors is actually using a linear combination of these. So write vector v with the components of 3, 7 as a linear combination. Of I and j. Anybody know what this is? I mean, what does it even mean if you haven't seen it before? Anybody want to give me the answer if you know it? It's actually super easy when you know what to do. Nicola? Yep. 3i plus 7j. And that's it. And just super quick, I can convince you that's true if you're like, well, that seems easy, but why? Let's plug in. We know that vector I just told you is 1, 0. And vector j is 0, 1. And then if we multiply by the scalars, we get 3, 0 plus 0, 7. And then when you add the corresponding components, you get 3, 7, which is what I told you vector v is. So that's why it works. So another way of notating the horizontal and vertical components is just as a linear combination of I and j. And then it's nice because when you're combining vectors, it's like combining like terms. So, any questions about that? So then let's get into our direction and magnitude notation. So direction and magnitude. And there's different ways. I mean, it's all equivalent. As I've seen this written different ways. If vector v has a direction, theta, and that is measured like we measure on the unit circle in standard form. So it is measured from the positive x-axis going counterclockwise. So if it has a direction theta, and we know that the notation for magnitude is that, Then another way we can talk about vector v, it's still the components, but when you write it this way, you actually can also see the direction and magnitude. So remember, x can be thought of as r cosine theta, and y is r sine theta. It's basically using that. Our r, though, is indicated by the magnitude. And then x cosine theta, y sine theta. So it just comes from that r cosine theta, r sine theta, though. So, with that said, I'm going to do, I think, we don't have time for both of these. You do have 2 word problems on your homework. I'll just say this. Do one of the 2. I'm going to do the more straightforward one. There's one with a weight. It talks about tension on the cables. I think given the time, and it's not necessary for the calculus that we're going to do, let's just skip that problem. I'll fix it in Canvas, so I'll make it only 1 word problem. But let's do the other classic kind of problem when you're first doing vectors, which is the plane flying in the air. We'll set it up. We probably won't have time to finish it, but we'll be able to set it up to get it going. So a plane, and I'll kind of shorten up the problem. A plane is flying at a bearing of 302 degrees. Airspeed is 900 kilometers per hour. Wind speed is 100 kilometers per hour from the southwest. What is the ground speed and direction of the plane? So basically, in the air, the plane is flying at 1 speed, and then the wind is either pushing it a little in the same direction, making it go faster when somebody's observing on the ground, or it might be pushing against them, which slows them down. And then somebody on the ground perceives that their speed is slower. So let's find out what's happening here. So I'm going to draw a picture here. The pictures that would actually be given to you, but I'm going to draw a picture. Actually, I don't need a coordinate. So when it talks about, actually maybe I will. When it talks about the plane flying at a bearing of 302 degrees, that means bearing is always measured like a compass. So don't worry, the diagram would be given. But on a compass, you start from the north direction going clockwise. So totally different from what we're used to in trig. So that means that the plane is flying in this direction. And you can think of this as 32 degrees right there. So this is the plane. And that's my vector. That's 900 kilometers per hour. But then the wind is blowing from the southwest. So it's blowing in this direction. In here, actually, we can put it right here. We'll do head to tail. And this is the wind. So the plane, the actual speed and direction of the plane can be indicated by this pink vector. This is not the greatest picture because everything's overlapping. But this is the plane trying to go in the direction. Mainly the wind is pushing it in this direction, so this is the resultant vector. This is what the plane ends up flying in. So we have to find the direction and length of that pink vector. So any questions about that? So we're just going to add two vectors together. So the plane, its magnitude is 900. It's the speed of the plane. What's the direction angle that we're going to use for the plane? Do you see it? Not 32. Think about where you have to measure from. Dylan? Was that a hand up? Oh, sorry. I thought that was a hand up. My bad. Oh, you were picturing it. Remember we had to measure from standard position. So this is 32 degrees, so this is 148 degrees. So that's what we're going to use for the plane. So cosine 148 degrees, sine 148 degrees. And then the wind, it's flying at a speed of 100 kilometers per hour, so that's our magnitude. And what's the angle for the plane? The wind. 45 degrees. So cosine 45 degrees, sine 45 degrees. So I'll just set it up, but we won't have time to finish it. But the resultant vector, you add those two vectors together. Now when you add the two vectors together, and I'll have it worked out so you can go back in the notes and take a look at it. But when you add the two vectors together, you're actually going to add whatever 900 times cosine 148 is plus 100 cosine 45. You're going to get a decimal. Just use that as your horizontal component. And then same thing for the vertical. But then you're going to have to use the formula that we know to find the magnitude. And then you can use this formula to help you find the just a minute.